hydrogen atoms. Okay. Mostly alkenes containing 6 to 11 carbon atoms. What are alkenes? Alkenes are the compounds having carbon atoms are linked together by only single bond. The general formula for alkane is CnH2n plus 2, where n is any number, any positive number. It may be 1, 2, 3, 4, 5, so on. So this is the simplest example of an alkane that is known as methane, CH4. Here you can see that carbon is making only single bond with the hydrogen atom. That's why these compounds are known as alkenes. And in gasoline, the alkenes may be present in the straight chain forms, branched forms, or may present in the form of isomers. And we have already discussed the isomers. Isomers are the two or more structures having the same molecular formula but different structure formula. For example, C5H12. As you can see that there is only 5 carbon atoms, so it will be known as pentane. Okay, pentane. So three possible isomers exist for pentane. Here you can see here that C5H12, same molecular formula, but we can write this pentane in different structural formula. This long chain form is known as N-pentane, N-normal pentane for long chain. This is known as 2-methyl-butane, also called as isopentane. This is a common name and this is the IUPAC name. And the third one is the 2,2-dimethyl-propane, also known as neopentane. Neopentane is the common name and the 2,2-dimethyl-propane is a IUPAC name, IUPAC, IUPAC name. As the number of carbon in the chain increases, the number of possible isomers increase rapidly. For example, for the decane C10H22, this will be called as decane. This is pentane for 5 carbon. This is decane for 10 carbon. 75 isomers are possible. So the number of isomers increase with the number of carbon atoms. Now, let's come to the point, gasoline. Gasoline contains several different isomers of octane. Now this is octane, an alkane having 8 carbon atoms are known as octane. Gasoline is burned in an engine. All of these compounds undergo combustion simultaneously, reacting with oxygen from the air and produce carbon dioxide and water as products with some amount of heat. It might be possible that some octane molecules don't react at all before leaving the engine, or some larger molecules have broken down into smaller fragments and made it into the exhaust, producing a sharp metallic sound called knocking. Keeping above the two possibilities, we can assume that gasoline can undergo two types of combustion. One is the complete combustion in excess supply of oxygen. All the carbon atoms are converted into oxygen. As you can see here that octane has reacted with excess of oxygen and converted into carbon dioxide and water. All the carbon atoms are converted into CO2, carbon dioxide. But there is another type of combustion which can be possible in gasoline, which is known as incomplete combustion, and it is possible only if insufficient oxygen is present. Then CO, carbon monoxide, a hazardous gas, is produced instead of CO2. C8H18 octane reacting with oxygen and in limited supply of oxygen and producing carbon monoxide instead of carbon dioxide, a hazardous gas with water molecules. So we can conclude here that a properly tuned engine ensures, or properties of a good engine is that it shows maximum complete combustion, low hazardous CO emission, and improves gas mileage. It means it does not produce any sharp metallic sound. So, what was the main reason of studying this combustion of fuel? Basically, we want to discuss that how much oxygen is needed to allow complete combustion to occur. So here we will use the concept of stoichiometry to discuss the complete combustion of a fuel. How much the amount of CO2 emitted relate to the amount of fuel burned. To answer this question, we will need to consider the stoichiometry of chemical reactions. Now, the stoichiometry. The word stoichiometry derives from the two Greek words stoichion, meaning element, and metron, meaning measure. So, it is a quantitative relationship between the amount of reactants and products in a chemical reaction, and it tells how much of a particular substance will be used or how much of a particular substance will be produced in a chemical reaction. So it will tell you how much of the reactant will be required and how much the product will be produced in the chemical reaction. The numbers used to balance a chemical equations are called stoichiometric coefficients. 2, 3, 4, the number that we use to balance a chemical reaction. So obtaining ratios from a balanced chemical equation. This is the start of our numerical problems. So you have to consider it more carefully. CH4, methane gas, reacting with oxygen gas and producing carbon dioxide and water molecule. One molecule of methane gas has, you can see here that one molecule of methane gas is reacting with two molecules of oxygen, or you can also say that one mole of methane is reacting with 2 moles of oxygen. Either you can consider it in the number of molecules, but more accurate, we will discuss in chemistry that a number of moles. So 1 mole of methane is reacting with 2 moles of oxygen and producing 1 mole of carbon dioxide and 2 moles of water. So we can write a different mole ratio as 1 mole of methane requires 2 moles of oxygen, or 1 mole of methane is reacting with 2 moles of oxygen. 1 mole of methane is producing 1 mole of CO2. 1 mole of methane is producing 1 mole of CO2. 1 mole of methane is producing 2 mole of water or 2 mole of oxygen. Here you can see 2 mole of oxygen is producing 2 mole of water. 2 mole of oxygen is producing 2 mole of water. And you can also write this 2:2 ratio in the form as 1:1 ratio. So these mole ratio are usually written like fractions. For example, 1 mole of methane is reacting with 2 mole of oxygen, then you can write it as 1 mole of methane divided by 2 mole of oxygen in a fraction form. 1 mole of methane, 1 mole of carbon dioxide. 1 mole of methane, 1 mole of carbon dioxide. 1 mole of methane, 2 mole of water. 1 mole of methane, 2 mole of water. 2 mole of oxygen, 2 mole of water. 2 mole of oxygen, 2 mole of water, or 1 mole of oxygen, 1 mole of water. So actually here I want to discuss that you can write the possible moles of reactant and products in the ratio form, or you can write these ratio forms in the fraction form. But here in my numericals, I usually prefer these ratio forms because they are more easy to understand and calculate. So let's start with example problem. And there are so many example problems here which are very important for exam's point of view. So you must have listened it carefully. In the combustion of methane, how many moles of oxygen are required? If 6.75 moles of methane is to be completely consumed. So here, the first step in this type of reaction is that first you have to write a balanced chemical equation. Okay. So sometimes the balanced chemical equation is given in the statement, but sometimes not. So you have to understand the reaction. Here you can see in the combustion of methane, it means it is the combustion reaction of methane. What is the combustion reaction? The methane is reacting with oxygen. Okay. So how many moles of oxygen are required? So oxygen is a reactant, methane is a reactant. Whenever methane and oxygen react with each other, they will produce carbon dioxide and water. We have discussed it earlier. So we have to calculate the moles of oxygen if 6.75 mole of methane is to be completely consumed. So you are given the moles of methane and you have to calculate the mole of oxygen required for the combustion of methane. So you can write it in the ratio form or you can write it in the fraction form. But in some examples, I will show you the two alternate methods this is the fraction form: 1 mole of methane reacting with 2 mole of oxygen, or you can write 2 mole of oxygen is reacting with 1 mole of methane. Both fractions are correct. But to calculate the desired amount of oxygen from the known amount of methane, we should use the second form, and this gives us the result needed. 2 mole of oxygen is reacting with 1 mole of methane multiplied by the mole of methane available, 6.75 mole available. It will give you an answer 13.5 mole of oxygen. This is a fraction method, but here I will more focus on an alternate method that is commonly used, that you have already studied this type of method in grade 4 or grade 5, and I usually use this method to teach my students at college level that find it very difficult to study this trigonometric calculation. When you understand this type of my method, this alternate method, then you will come to know that this is a very easy method, and you can solve every type of question that you encounter in your exams. So first, you will have to write a balanced equation: CH4 methane reacting with oxygen and producing carbon dioxide and water. This is a balanced chemical equation. 1 mole of methane requires 2 mole of oxygen. 1 mole of methane requires 2 mole of oxygen. So 6.75 moles of methane will require 2 multiplied by 6.75. It will give you 13.5 moles of oxygen. Hence, 16.75 moles of methane will require 13.5 moles of oxygen to burn completely, to be burned completely. This is the answer, and this is the more easy method as compared to the previous one. How many moles of water will be formed in a reaction above? Now here you have calculated the number of moles of oxygen required for 6.75 moles of methane, and in this reaction with this data you have to calculate how much moles of water will be produced. So 1 mole of methane is producing 2 moles of water. So 6.75 moles of methane will produce 13.5 moles of water. Again, the same statement: 2 multiplied by 6.75, 13.5 moles of water. If you want to use the oxygen in place of methane, then you can also get the same result. For example, 2 moles of water is producing 2 moles of water. 2 moles of oxygen is producing 2 moles of water. And here we have calculated that 13.5 moles of oxygen. So the 13.5 moles of oxygen will produce 13.5 moles of water. So again, from both, either you will start with methane or you will start with oxygen, you will get the same answer of your product. So you can use any of the reactant to get your final result. Now another example problem. We have considered a reaction between hydrogen and oxygen to form water. How many grams of water can be produced? Now we have to calculate grams, mass of water, not the number of moles of water. So we have to proceed this explanation to further one step to calculate the mass of water that can be produced if sufficient hydrogen reacts with 26 gram of oxygen. Now the mass of oxygen is given, which is 26 gram, and with the help of this amount of mass, we will calculate the number of moles of oxygen. So first, we will write a balanced chemical equation: 2H2 plus O2 changed into 2H2. This is the reaction between the hydrogen and oxygen. Now the given mass of oxygen is 26 gram, and with the help of this, we will calculate the number of moles of oxygen by calculating its molar mass, which is the 32 gram per mole. Atomic mass of oxygen is 16 multiplied by 2, as there are 2 atoms, so 32 gram per mole. Now the formula is N, number of moles, is equal to mass divided by molar mass. So this is the given mass, 26 gram, divided by 32 molar mass, and the answer will be 0.81 moles. Now to come to the statement: 2H2 plus O2 changed into 2H2. 1 mole of oxygen is producing 2 moles of water. 1 mole of oxygen is producing 2 moles of water. Then 0.81 mole of oxygen will produce how how much moles of water? Obviously, 2 moles of water multiplied by 0.81 moles of water, it will give you answer 1.62 moles of of water. This is the number of moles of water. Sorry, I will say here you have to write H2O. This is the number of moles of water. Now you have to calculate, as you can see here, how many grams of water, not the moles of water. You have calculated the moles of water. Now you have to move forward for the second step, which is calculation of the mass from the number of moles. And this is the formula. M is equal to mass divided by molar mass. Mass divided by molar mass. The molar mass of water is 18 grams per mole. So multiply this molar mass with this number of moles, we will get this equation, mass in grams. So use this equation, number of moles of water 1.62 moles multiplied by molar mass of water 18 grams per mole. Then you will get the answer, mass in 29.3 grams of water. Hence 26 grams of oxygen will produce 29 grams of water. This is the stoichiometric calculation. This whole lecture is full of examples and problems. So no need to worry, these are very, very easy. Now in the same statement, you have to calculate the mass of hydrogen needed to produce 29.2 grams of water. Again, start with the Valence equation. The given mass of water 29.2 grams. You have to produce 29.2 grams of water. Now you are going to calculate the reactant from the given amount of product. That how much you will require reactant to produce that particular amount of product. For this, you will have to convert this mass into number of moles. Now you have calculated number of moles, mass over molar mass, and after this calculation, you will get the answer 1.62 moles of water. Now this equation, from this equation, we are going to write the statements. 2 moles of water requires 2 moles of hydrogen. 2 moles of water requires 2 moles of hydrogen. 1 mole of water will require only 1 mole of hydrogen. So 1.62 moles, as you have calculated here, 1.62 moles. So 1.62 moles of water, your product will require only 1.62 moles of water. Same ratio, 2:2 ratio. So this will be the only same ratio, 1.62 moles of water. Now you have to calculate the mass of hydrogen. So again, the same formula. Multiply this number of moles with the molar mass of hydrogen. Number of moles of hydrogen 1.62, molar mass of hydrogen 2.016 gram per mole. So mass of hydrogen question mark. So mass of hydrogen, as you can see here, n number of moles is equal to mass over molar mass. Multiply this molar mass with this n multiplied by m, then you will get the small mass. So mass of hydrogen is equal to number of moles of hydrogen, just like this, multiplied by molar mass of hydrogen, which is 2.016 gram per mole, and after multiplication we will get answer as 3.27 gram of hydrogen. Hence 29.2 gram of water will require 3.27 grams of hydrogen. This is your answer. Another problem. Tetraphosphorus trisulfide P4S3 is used in the manufacture of Stoichiometry matchbox. So elemental phosphorus and sulfur react directly to form P4S3. 8P4 plus 3S8 changed into 8P4S3. Now the Valence chemical equation is given by this example problem. So we have 153 gram of sulfur 8. This is the octa-atomic sulfur. This is the another, or you can say this is the allotropic form of sulfur, in which consists of 8 atoms of sulfur arranged in a crown shape, just like a crown of a king. So these sulfur atoms are arranged in a circular manner in the shape of a crown, and it reacts with excess of phosphorus. Now phosphorus is present in the excess amount. So what mass of P4S3 can be produced by this reaction? Now you have to calculate the expected amount of product from the given amount of reactant. So after writing the balanced chemical equation, we will calculate the number of moles of sulfur from this given mass of sulfur. 153 given mass divided by its molar mass. The atomic mass of sulfur is 32. 32 multiplied by 8. As you can see, this is octa-atomic, 256 gram per mole. Mass divided by molar mass. Then we will get 0.598, about 0.60 moles of S8. Now, the balancing of equation. 3 moles of S8, 3 moles of S8 produce 8 moles of P4S3. 1 mole of S8 will produce 8 divided by 3. Now, divide this 3, take this 3 here, and 8 is divided by 3 moles of P4S3. Now, 0.60 moles of S8 will produce, then you have to multiply this mole ratio with 0.60, then you will get the answer 1.6 moles of P4S3. This is the most important part of your answer, so revise it carefully. As we know, number of moles mass over molar mass. Now the moles are given, and you have to calculate the mass of P4S3, the amount of product. So you will calculate the number molar mass from the formula. Phosphorus atomic mass is 31, the sulfur atomic mass 32, and after calculation we will get 220 gram per mole. So multiply this molar mass with the number of moles that you have calculated from this statements, and you will get the answer 352 gram. Hence, 153, the given amount of S8 can produce 352 gram of P4S8. Now, the smell of a burning match is due to the formation of the sulfur oxides. We can represent the relevant reaction as sulfur reacting with oxygen producing SO2. If 4.8 gram of sulfur is burned in this manner, now reactant, the amount of reactant is given, and you have to calculate the amount of product produced in terms of its mass. Sulfur plus oxygen changed into sulfur dioxide. Mass of the sulfur is given 4.8. Now you have to calculate the number of moles. Mass divided by molar mass changed into 0.15 moles. 1 mole of sulfur will produce 1 mole of sulfur dioxide. Then 0.15 moles of sulfur will produce 0.15 moles of sulfur dioxide. Now you have calculated the number of moles of sulfur dioxide. Now you have to calculate the mass of sulfur dioxide, and for this you have to calculate the molar mass of sulfur dioxide, which is as follows. Sulfur atomic mass 32, oxygen atomic mass 16, multiplied by 2, 32. 32 plus 32, 64 gram per mole. So this is the molar mass of sulfur dioxide. Now M is equal to M over M, mass divided by molar mass. Multiply this molar mass with number of moles, then you will get the mass of the of your product. Number of moles multiplied by molar mass. Number of moles 0.15 moles, as you have calculated in this statements. Multiply by its molar mass. Here you have calculated this molar mass. Then you will get answer 9.6 gram. Hence 4.8 gram of sulfur will produce 9.6 gram of sulfur dioxide, which is your product. Now we have understood that how to calculate the amount of product that can be obtained from a reaction and the amount of reactant that is required to produce a particular amount of product. Now we are going to discuss a new concept which is known as limiting reactant, and this is very important for our chemical, for every chemistry student, either it is a chemical engineer or just a chemist. So the reactant completely consumed in the reaction is called as limiting reactant, or you can say the reactant that is consumed earlier. If there are more than one reactant, then the reactant that is consumed earlier will be the limiting reactant. Or you can say the reactant that controls the amount of product is called limiting reactant. Suppose we start with 6 molecules each of hydrogen and oxygen. For example, you have 6 molecules of hydrogen and 6 molecules of oxygen, and you allow them to react. So water can be produced as follows: 2H2, 2 moles of hydrogen reacting with 1 mole of oxygen to produce 2 moles of water. So 1 mole of oxygen requires 2 molecules of hydrogen that produces 2 molecules of hydrogen. Now the available number of molecules is only 6. Number of molecules of hydrogen available 6. Number of molecules of oxygen that is available 6. But according to this equation, you can see that 6 molecules of oxygen will require 12 molecules of oxygen that will produce 6 molecules of water. But available number of molecules is only 6. So only 3 molecules of oxygen. So only 3 molecules of oxygen will react with 6 molecules of hydrogen, and 3 molecules of water will be produced. After 6 molecules of water have been formed, all the after 3 molecules of water, after the formation of 3 molecules of water, all the hydrogen will be consumed, even though 3 more molecules of oxygen are left behind. Means oxygen was in excess and hydrogen was in limited amount. So the amount of product formed is limited by the amount of hydrogen that was available. It was only 6. And we say that hydrogen was the limiting reactant because it limits the amount of product. So here you can understand the three terms of a limiting reactant. The reactant completely consumed in the reaction. So you can see here all the hydrogen molecules have been consumed. The reactant that is consumed earlier, so you can see the hydrogen has been consumed earlier than the oxygen. That controls the amount of product. As you can see that the amount of product formed is limited by the amount of hydrogen. So hydrogen is the limiting reactant. Now start with another example. A solution of hydrochloric acid contains 5.22 gram of HCl. Now you can see 5.22 gram of HCl, which is allowed to react with 3.25 gram of solid potassium carbonate. And the products are KCl, CO2 and H2, which reactant is in excess. Now you have to find out the excess reactant and the limiting reactant. Now you have to write the Valence chemical equation on your own. We know the reactant and products. So we can write a skeletal equation easily. HCl reactant, potassium carbonate reactant, converting into KCl, CO2 and H2. After balancing the equation, we will get 2HCl plus K2CO3 changes into 2KCl plus CO2 plus water. Let us use the quantity of HCl given and calculate the amount of K2CO3 that would react completely with it. So we will start with the first one, HCl. So we will calculate that how much K2CO3, how much potassium carbonate will be required with this amount of HCl to completely forward the move the reaction. So then at the end we came to know that if the potassium carbonate is in excess, then we will get HCl is a limiting reactant. If we came to know that HCl is requiring more potassium carbonate and this is the less amount, so we can to know that potassium carbonate is a limiting reactant. Here you can understand this explanation. Mass of HCl given 5.22 gram, molar mass 35.5 chlorine and plus 1 hydrogen 36.5 gram per mole. Number of moles of HCl, mass divided by molar mass, 5.22 divided by 36.5, and you will get 0.14 moles of HCl. Now we are going to calculate the limiting reactant, that how much mass of potassium carbonate will be required by this moles of HCl. Now 2HCl potassium carbonate change into 2KCl plus CO2 plus H2. 2 moles of HCl requires 1 mole of potassium carbonate. Here you can see 2:1 ratio. Or you can do it in the form of ratio, which is more easy and more time saving, to HCl carbon potassium carbonate. So 2 moles of HCl requires only 1 mole of potassium carbonate. Then 1 mole of HCl will require only 1 by 2, means 0.5 moles of potassium carbonate. Then 0.14 moles of HCl will require only 1 point divided by 2 multiplied by 0.14 moles of potassium carbonate, and we will get the answer as 0.07 moles. Unit should be mentioned in writing your statement, and, which is shows that this is the number of moles, and this is the unit moles. So number of moles of potassium carbonate is 0.07. Molar mass of potassium carbonate is, as I have calculated here, potassium atomic mass 39, carbon 12, oxygen 16, which is 138 gram per mole. Now you have to calculate the mass of potassium carbonate from this given number of moles that you have calculated from this quantitative relationship. So multiply this number of moles with this molar mass, and you will get the answer as 9.66 gram of potassium carbonate. But the available amount of potassium carbonate was only 3.25 gram. But HCl, this amount of HCl is requires 9.66 gram potassium carbonate. So the given quantity of HCl 5.22 gram requires 9.66 gram potassium carbonate, but we have only 3.25 gram of potassium carbonate available. So the reaction will stop once all of the potassium carbonate is consumed. Hence, potassium carbonate is the limiting reactant and HCl is in excess. Now, another problem. Ammonia is widely used in the production of fertilizers and also the precursor to a number of important polymers. So the formation of ammonia from its element is one of the most important industrial chemical reactions, and ammonia is normally produced by Haber's process, very famous procedure for the synthesis of ammonia, and we will discuss the complete structural diagram of this Haber's process in the further semesters. Ammonia reacting with hydrogen to produce ammonia. This reaction is usually carried out using excess of hydrogen. If a reaction vessel contains 1.5 into 10 raised to power 3 moles of nitrogen, how much hydrogen would be needed to ensure that it will be in excess? Now, you have to ensure that the hydrogen should be in excess. So first, you will have to find out that these moles of nitrogen, 1.5 into 10 raised to the power 3 moles of nitrogen, that how much hydrogen is required by this amount of nitrogen. Then you will come to know that the amount of hydrogen must be greater than this calculated amount of hydrogen to ensure the excess amount of hydrogen. Now let's start with the solution. Now let's start with the ratio form, which is more convenient and easy to discuss and time saving. Nitrogen, hydrogen. Nitrogen is 1 mole, hydrogen is 3 moles. 1 mole of nitrogen requires 3 moles of hydrogen. Then 1.5 into 10 raised to power 3 moles of nitrogen will require multiply by 4.5 into 10 raised to power 3 moles of hydrogen. Now from the moles of hydrogen, now 1.5 into 10 power 3 moles of nitrogen will require 4.5 into 10 power 3 moles of hydrogen. From the number of moles, you will calculate the mass of hydrogen. How? Just multiply the number of moles with its molar mass by using this formula. Multiply by molar mass 2.016 gram per mole, you will get 9.07 into 10 to the power 3 gram, which is equal to kilogram. So the amount of H2 should be greater than 9.07 kilogram, which is because this is the amount of hydrogen that is required by this amount of nitrogen. So in order to assure the excess amount of hydrogen, the amount of hydrogen should be greater than 9.077 kilogram to ensure its excess. Now another question problem. We use a reaction that produces P4S3, one of the reactants in the combustion of a match. If 28 limiting reactant. So here let us calculate the number of moles of P4. Here you can see that this is the given amount of phosphorus. From this amount of phosphorus, from this mass, you will calculate the number of moles. How? First, you have to calculate the molar mass. Atomic mass of phosphorus is 31, as it is P4. So multiply it with 4, you will get 124 gram per mole. Mass divided by molar mass, 28.2 divided by 124 mass divided by molar mass, you will get 0.23 moles. Now, with the help of we will calculate the number of moles of sulfur S8, 18.3 gram of S8. You don't have to calculate. You don't have to find out which one is the limiting reactant. This statement has already given you the answer that S8 is the limiting reactant. So just you have to find out the amount that can be produced, the amount of product that can be produced from this limiting reactant. So you have to calculate the number of moles of sulfur also. Mass 18.3 gram, molar mass it multiply by 32, 256 gram, mass divided by molar mass, and you will get answer 0.07 moles. 8P4 plus 3 S8 change into 8P4 S3. So we will use the mole ratio as P4 S8. 8 moles of P4 is reacting with 3 moles of S8. 1 mole of P4 will react with 3 divided by 8. Here you will divide this 3. You will divide this 3 by 8. Then 0.3 moles, 0.23 moles of phosphorus. 0.23 moles of phosphorus will require 3 divided by 8 into 0.23. Here you will multiply 0.23 with this mole ratio, and you will get answer 0.0866 moles. So 0.23 moles of phosphorus, here 0.23 moles of phosphorus requires only 0.086 moles of sulfur. But we have only 0.07 moles of sulfur, as you have calculated from this amount. 18.3 gram of sulfur was only 0.07 moles, but your requirement is 0.086 moles. There is not enough S8 to react completely with all P4. Therefore, S8 is the limiting reactant. Now, another example problem. MTBE, methyl tertiary ether, has been used as an additive in gasoline, and thus compound is produced by reacting methanol and isobutene according to the following equation. This is the methanol, this is the isobutene, and this is producing MTBE, methyl tertiary ether. If 45 kg of methanol is allowed to react with 70 kg of isobutene, what is the maximum mass of MTBE that can be obtained? So first you have to find out which one is the limiting reactant, either methanol or isobutene. Once you find out which one is the limiting reactant, then you will calculate the amount of MTBE that can be produced from that limiting reactant, either it is methanol or isobutene. Solution. We will need the molar masses of all three compounds. So taking care to interpret the molar masses, we have calculated molar masses of all the three chemicals, methanol, isobutene, and MTBE. First, we will calculate the number of moles of methanol. Mass of methanol 45, molar mass 32.042. This is the mass of methanol 45 kg, which is given in the statement, 45 kg of methanol. Now, number of moles mass divided by molar mass, and it is 45 divided by 32.042, and it is 1.40 moles. Now, you have to find out the limiting reactant in this equation. Methanol with isobutylene changed into MTBE. Now, methanol and isobutene, 1:1 ratio. 1 mole of methanol is reacting with 1 mole of isobutene. That 1.4 moles of methanol will require only 1.4 moles of isobutene, 1:1 ratio. So 1.4 moles of methanol requires 1.4 moles of isobutene. Number of moles of isobutene N is equal to 1.40 moles. Molar mass is 56.107. Just multiply this number of moles with this molar mass and you will get the mass 78.54 grams. And you can see here the available amount of isobutene was 70 kilograms, but the actual requirement was 78.54 grams. This tells us that to use 45 kilograms of methanol, we need at least 78.54 kilograms of isobutene. But we have only 70 kilograms of isobutene, so the amount of isobutene available will determine the amount of MTBE because isobutene is the limiting reactant. Isobutene is the limiting reactant and methanol is in excess. Now the problem is reduced to a simpler stoichiometry calculation starting from the mass of isobutene available. So the isobutene is limiting reactant. So the maximum mass of the MTBE, your product that can be obtained from this isobutene, will give you the overall yield of your reaction. So 70 kilograms of isobutene. The available mass of isobutene, is 70 kilograms and the molar mass is 56.107. Number of moles, mass over molar mass, then you will get, this is 70 kilograms, 70,000 grams divided by 56.107, and you will get 1.25 into 10 to the power 3 moles. From the equation, mole ratio, isobutene, this is the limiting reactant, and you have to find out that how much product will be produced from this limiting reactant. As 1 mole of isobutene is producing only 1 mole of your product, then 1.25 into 10 raised to the power 3. Sorry, this is not 2 here, this is 3 here. So 1.25 into 10 to the power 3 moles of isobutene will produce 1.25 into 10 to the power 3 moles of your product. So 1.25 moles of isobutene will give 1.25 into 10 to the power 3 moles of MTBE. Then you have to calculate the mass of your product from this number of moles, and you will use this universal equation, molar mass multiplied by number of moles, and you will get mass of your product. This is the number of moles, this is the molar mass, and after multiplication you will get 110,186.25 grams, which is equivalent to 1.1. And how many decimal position we have shift from this to this? 1, 2, 3, 4, 5. 5 decimal places, 5 dp. So here you can write it as 1.1 into 10 raised to the power 5 gram. 1.1 into 10 raised to the power 2 kilogram. I have converted this gram into kilogram. 1 kilogram is equal to 10 raised to the power 3. 10 raised to the power 3, 10 raised to the power 2 means 10 raised to the power 5. So both are equal. Now we have another question problem, and I think this is the last one. The compound diborane B2H6, this is known as diboranes, just like alkenes, was once proposed for use as a rocket propellant. It can be produced by the following reaction: lithium boron hydride. Lithium boron hydride, it is a reducing agent reacting with boron trifluoride to produce borane, diborane, and lithium fluoride. Now, if 24.6 gram of lithium boron hydride reducing agent is combined with 62.4 gram of BF3, what mass of diborane can be formed? Now, again, you have to find out which one is the limiting reactant. Either it is lithium boron hydride or it is BF3. Then after finding the limiting reactant, you will calculate the mass of the product from that limiting reactant. So we will start with this. Try to find out the limiting reactant. Mass of lithium boron hydride mass is equal to 24.6 grams. Molar mass is equal to lithium boron hydride. lithium atomic mass is 3, boron 5, and 4 hydrogen. 4 multiplied by 1. Then you will get 12 gram per mole. Lithium 3, boron 5, hydrogen is 1. Number of moles N is equal to mass divided by molar mass. Number of moles of lithium boron hydride get mass divided by molar mass. This is the mass, available mass 24.6 grams divided by molar mass 12 gram per mole. Then you will get 2.05 moles. Now you have to find out the number of moles of BF3, boron trichloride. Now, here directly we will calculate the BF3 that is required by 0.05 moles of lithium boron hydride. Lithium boron hydride. In equation, there are 3 moles of lithium boron hydride requires only 1 mole of BF3. So 3 moles of lithium boron hydride requires only 1 mole of BF3. 1 mole of lithium boron hydride will require only 1 divided by 3 BF3. Then 2.05 moles of lithium boron hydride will require only 1 over 3 multiplied by 2.05, and it will give you an answer 0.683 moles of BF3 will be required by 2.05 moles of lithium boron hydride. Now from this moles of BF3 you will calculate the mass by multiplying this moles of BF3 by its molar mass. This is the formula how we calculated the mass from the given number of moles, and this is the molar mass, how you calculate the molar mass of the BF3. Atomic number of boron is 5, atomic mass. Fluorine atomic mass is 19. 19 multiplied by 3, 57 plus 5, 62. So multiply by 62 with number of moles 0.683, you will get answer 42.346 grams. So 24.6 gram of lithium boron hydride. As you can see here, the available mass of lithium boron hydride is 24.6 gram. So 24.6 gram of lithium boron hydride requires only 42.346 gram of BF3. Available amount is 62.4 gram. Here you can see the available amount of BF3 is 62.4 gram, which is much greater than this 42. So BF3 is in excess and lithium boron hydride is a limiting reactant. Now calculate the amount of product that can be formed by limiting reactant. Now this is the limiting reactant, lithium boron hydride. Now this will tell you the amount of product that can be obtained in this reaction. Lithium boron hydride, and this is your product, boron. This is limiting reactant and this is your product. 3 moles of lithium boron hydride is producing 2 moles of diboron. Here you can see 3 moles of lithium boron hydride is producing 2 moles of diboron. 1 mole of lithium boron hydride is producing 2 divided by 3 moles of diboron. Then 2.05 moles of lithium boron hydride will produce 2 divided by 3 into 2.05 will give you answer 1.36 moles of diboron. Here you can see that 2.05 moles, or you can say that the available amount 24.6 gram of lithium boron hydride will give you only 1.36 moles of boron. And I think here I have one more step, and this one step is that you have to calculate the mass of diboron from these number of moles. Just you have to multiply this number of moles with the molar mass of diboron, then you will get the mass of the diboron that can be obtained in the reaction. So just revise all the numerical problems and let me know if you find any problem or any difficulty in any step. I will repeat the whole numerical or whole equation for you anytime.